YouTube here, it says live
You're on,
in
Alex.
7 minutes.
You're on, Alex.
Hi, everybody. This is Alex from the Astroimaging channel. Welcome back, everybody, to our Sunday night get-together where we talk about astroimaging. And we ask questions, and we find out what's happening in astroimaging. And tonight, in particular, Dr. Dave Doctor, will be joining us from Las Cruces, New Mexico. He's here to tell us about high-res spectroscopy. And we're looking forward to that show, find out some things we can do as astroimagers besides take pretty pictures, where we focus a lot on that kind of stuff. So let me take you over to the website for a minute, because I got to remind you of some things. First place, I want to remind you that we've got a big spreadsheet out there with all our programs in it. And we've got a couple of people working really hard to put information into this spreadsheet. You can search anytime you want and find whatever it is you like, and it's a description of programs and all that we've had. And we've gotten like a couple of years worth done now, and we're coming up on what, 8 years or 7 years, 7 full years. And it's been hard to get it all caught up, but Wanda has gotten us caught up, and she's starting to get some other people to help. If you'd like to help on this project, you can see that down towards the end, we've got lots of them down towards the end that aren't done yet. I'd also like to congratulate Wanda, who didn't join us in the room tonight because she's moving around the country, but she's with us, I think. Wanda, you got a letter to the editor in Sky and Tel magazine, if I'm not mistaken. So congratulations on that. Now, where were we? Oh, yeah, we were going to go, told you about that. And I want to tell you about the calendar because tonight's Dave, and then next week we won't see you because we have to be jumping up, and it's my time, 6:30 at night here in California. I'd be out there feeding the ghouls and the skeletons and stuff like that. So I'm not going to be able to be here. So there's not going to be a TAIC show next week. So you'll all be on Sugar Rush anyway, and you probably wouldn't be contributing to the program. So we're just going to skip next week. But Deborah Ceravolo is joining us, and Deborah's always a pleasure to have around. I'm going to stop sharing because Deborah's here, and she's going to tell you just a little bit about what's happening with that program. Stop sharing. Sure. Deborah, come on in.
Sure. Can you hear me okay?
Yep, we're going fine.
Okay. Yeah, I'm going to be talking about how I acquire my narrowband images for emission nebulae and how I process them. And basically the bottom line that, the results I got from all the testing that I did with different filters is actually quite surprising even to me. But the result is that basically forget RGB, use only narrowband, but I use other filters like hydrogen beta. That makes all the difference in the world. So tune in to find out more about that.
Okay, thank you very much, Deborah. We'll be seeing you now. That's in a couple of weeks, remember. Because we're going to be gobbling next week, not gobbling Thanksgiving. That's in a different time coming up. And then, where were we? Then we've got some other programs, and then we start having emptinesses, and we've got to fill those empties, and we need your help doing that. So please hit the contact button. Okay, tell us who you are, what you want to talk about, and join the fun. It's good to have people that are really, 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 really professional, high class, everything. But mostly we want people that are enthusiastic about astroimaging and are willing to join us, okay? So please come along with that. And if I'm not mistaken, let's see, there it is. Oh, I have to turn myself off. There we go. You got notice over here, you've got an area to ask questions about spectroscopy tonight. If you've got anything that you want to know, you've got some buttons. You can donate, and you can put in some emoticons. You can do all that kind of stuff. You can buy swag for Christmas presents, really cool Christmas presents. So there's all sorts of stuff here, but mostly join in the conversation over here. It's part of what we do. We're a little different than the other programs. We've got one fellow that keep asking us, why do we keep interrupting the presenters? Well, we should tell you, we ask the presenters before each show about whether they prefer to be interrupted or everything held. And almost invariably they say, no, when a question comes up, if it's appropriate, bring it up. We do wait until there's a logical break to bring it up. But if you've got a question, like see what Astro Molly says, she put that big red question mark in there and put it in. Now tonight's one of the nights where the presenter has asked us to hold off till the end. So get your questions in, but don't expect us to be interrupting like that. But anyway, that's why we feel it's necessary to interrupt. We're not like some programs where we've just got somebody that's going to get up there and talk the whole way through. It's somewhat interactive. That's why we rely on this information over here. Okay, but enough about how we run the Astroimaging channel. Let me stop sharing my screen. And Dave, are you about ready to come on back in with us?
Yes, sir.
Okay, Dave, you go take it over. Tell us who you are, what you're about, and why we should be doing spectroscopy.
All right, thanks very much. Let's see if we're good here.
You're looking good.
Okay.
And yep, there you go. You're pulling on. Cool.
All right. Well, greetings from Las Cruces, New Mexico, and that is actually located about 3 hours south of Albuquerque and 4 hours east of Tucson. And I just want to thank you guys for the opportunity to share something that's a little different than what you may be used to here on this channel. We are going to boldly go where few astro-imagers have gone before, and that's into the realm of spectroscopy, and specifically high-resolution spectroscopy, which is growing in popularity. I would say it's hugely popular in Europe, not as much in North America, but I think it is gaining some traction here as well. And so what I wanted to do is just kind of give you a soup to nuts general overview of what it is, why you might want to do it, and if you did decide to do it, how you would go about doing that. So just a little background on why I decided to be here. I apologize for the truncated caption on the bottom of the image here. This was the Sacramento Mountains Spectroscopy Workshop, which was held in Las Cruces, I think about 2 to 3 years ago. You can see me under the black arrow in the back there. But I am mostly an astro-imager, like many of you. I do remote imaging. And about, I would say, 10 years ago, I started playing around with the star analyzer, which is a low-resolution grading some of you may be familiar with. And I was frankly amazed at the stuff that you could see with such a simple setup. But I really wondered, well, what the heck is this high-resolution thing about? And so I got a spectrograph, and a couple of friends of mine who were avid spectroscopists, and they were responsible for putting on this conference. They approached me and they said, "Hey, do you know anybody who has equipment? Because we really need somebody to do a demo for this conference." And I said, "Yeah, I got equipment. Haven't used it yet, but I have it." So I volunteered and realized just after that, gee, I only had a couple months and I was going to have about 150 people at my house. So I better figure this out pretty quick. And I was able to do that and learned a ton. And, after that, I thought to myself, gee, that's really not that hard. In fact, I was surprised and felt that doing like high resolution regular imaging really is a lot less forgiving. And so I decided to, share some of the stuff I learned, and hopefully at the end of this, at least one or two of you might get the same impression and they want to try it out. So I thought this was a great audience because you guys already know how to do pointing and tracking. You know about polar aligning, collimating. You know how to use a guide camera. You know how to use planetarium and camera software, and you understand the basics of image calibration. You're already 95% of the way there. So that's certainly one reason why you might want to think about it. I'm an imaging fanatic like a lot of you, and it never gets old. I get that. But look, after your 800th Pleiades and your 700th M31 and your 600th Orion Nebula, maybe you might ask yourself, gee, is there something else I could do that won't necessarily take away from my imaging schedule completely, but something that's interesting and fun that, I could do on the side. And yeah, there definitely is something you can do. You might be in a situation where you're in a Bortle 50 sky and there's no way you're going to get to a dark sky site anytime soon. The moon is not our friend for 2 weeks out of the month. But and you may be getting tired of, the Hubble palette, for example. But the great news is that spectroscopy doesn't really care about ambient light, surprisingly. In fact, this setup on the left here is a amateur spectroscopist who is in Paris and has her set up about a block away from the Eiffel Tower. So you can imagine what that's like. Do you have to understand vector calculus and quantum mechanics? No, you don't have to understand any of that. And I've been doing this for a few years, and I still don't understand it. One of the most compelling reasons for doing it is that you are virtually guaranteed to participate in a direct, meaningful way to astronomy research and discovery. And it's one of the few areas in our hobby that's still a possibility. This was a project I did on the relatively recent nova outburst. I know some of you were imaging, and I got kind of late. I was a little late to the party, about maybe a week and a half after the peak. But I was excited because a lot of novae are pretty dim, and you really can't do much with them. But this one was bright enough where I was able to take a couple of spectra, and I submitted it. And a couple of days later, it was part of an astronomical telegram. So this is a definite. This is something that you will be able to do on a regular basis, pretty easily. If you become a member of the American Association of Variable Star Observers, you're going to get bulletins from them every couple of weeks, and there'll be plenty of projects. Believe me, the professionals need your data. They're going to bug you for it once you get involved with this. So there's not going to be any shortage of work. One of the reasons I like it is it's kind of it's relaxing for me, because for those of you who do remote imaging, I'm sure you can relate to being anxious about things like software crashing and cameras timing out, and your roof doesn't close, and the internet drops, and it can be really stressful. This is really great because it's all hands-on. It's a very simple setup. I have a home-built roll-off in my backyard in Las Cruces. I just set my laptop up on the shelf. I've got my spectrograph here on the left. I use a C14. The projects are super short. They're like maybe an hour or two. And the processing literally is like about 20 minutes, as opposed to a minimum of 20 hours with PixInsight and Photoshop. So what is spectroscopy? Well, a lot of what we know about how the universe works comes from spectroscopic observations. The simple diffraction of light into its component colors or wavelengths gives astronomers the ability to figure out a host of physical properties of whatever they're looking at. And this can be anything from velocity, temperature, mass, and a host of dynamic processes that are occurring in the object. For us as amateurs, we're focused on the visible light, which is from about 4,000 or so angstroms to around 7,000. On the right here, you see this is a low resolution spectrum I took of, I think it was Vega, or it was a spectral type A star, and I don't know if you can see this, or these little vertical black lines. These are absorption lines. And on the bottom here, this is a typical spectral plot where you have intensity in the y-axis and the wavelength is in the x-axis, and you get these little dips here, which are the absorption lines that occur at discrete wavelengths. And if these were emission lines, they would be flipped and the intensity would be increased at the same locations. There basically are three different types of spectra. On the left is what's known as a continuous spectrum. That's produced by a very hot, opaque body, like the inner photosphere of a star, and you get a spectrum without any lines in it. If you have an intervening layer of gas that's cooler, that's going to absorb the light or the energy from the inner photosphere, and that's going to cause a superimposition of the absorption line on the continuous spectrum. And in the case of an emission spectrum, you're going to have a hot low density gas kind of by itself with nothing between it and you, and that's going to give you an emission line. All the elements that we know have this sort of barcode of potential spectral lines based on their atomic structure, and those potentially could give you absorption or emission lines depending on what's happening. So what is high resolution spectroscopy? Well, that's similar to, in a way, to regular imaging, where, for example, you have your 500 millimeter focal length wide field setup where you're taking the, beautiful Milky Way shots and nebula shots, and then you got your 0.5 arc second per pixel galaxy images. So here, what we see on the left is a low resolution spectrum, what I showed before. And if you take this hydrogen alpha absorption line here and you blow it up using high resolution equipment, you can see all these little lines here in the line profile. This is about 100 angstrom field, as opposed to a 3,000 angstrom, the whole spectrum that you see with the low density setup. So you can imagine that subtle changes in this line profile could indicate a host of events, anything from mass ejection in the star to maybe interaction with the binary. A lot of processes that occur on these objects are figured out just by these small alterations, or sometimes they're huge, like in the case of a nova. But more information that can be gathered from these single absorption lines than you might think. In a spectrograph, which is the instrument we use, the resolution is determined by the number of lines in your diffraction grating, which is basically a block of glass with a bunch of etched lines in it. So in a high resolution setup, you have maybe 2,400 lines per millimeter, and a low resolution might be like 100. In the spectroscopy world, the R value is the resolution, and that's defined as the wavelength you're looking at divided by the smallest wavelength increment that you can resolve. So for a low resolution setup, you're going to be able to see maybe 66 angstroms as your smallest detail, but in a high resolution, it goes up to, or down to, like 0.4 angstroms, that's a pretty big difference. So what equipment do you need? So for myself, look, I'm not a mechanical engineer. I'm not an electrical engineer. I'm just an old country doctor, Jim. So I kept it simple. I didn't want to reinvent the wheel. This is the Lhires 3, which is manufactured by Cheliac Instruments in France. And the L stands for litro, which is a type of spectrograph design that it has. Don't have enough time to go into the different ones, but needless to say that for this unit, everything is there. You've got your guide port, so you don't need an extra guide module. You have both your calibration lamp and your flat lamp are already in there. You've got your micrometer that you can scroll to different parts of the spectrum. And it's pretty much ready to go right out of the box. Now there are other options if you are mechanically inclined. There are spectroscopy groups that actually are 3D printing their own spectrographs, and there are kits available, so there are plenty of options for just about any type of background. It's a very interesting setup. You can kind of think of it in a way as like a mini folded refractor. So you have your light that comes in from the telescope. It goes down to this reflecting slit here. That's what it's called. There's a 23 micron slit that's in the that bisects this thing, and so you have light that reflects off of that onto this mirror and into your guide camera, and the rest of it, or the portion of it, the small portion of it going through the 23 micron slit, goes to your acquisition camera, and it bounces off of the diffraction, the reflection grating, back through this 30 millimeter doublet lens onto your CCD. Now there is a tilt here of about 10 degrees. Otherwise, the slit image would just go back out to the sky, and that really wouldn't help us too much. But the one thing you really want to get from this diagram is that your camera, your acquisition camera here, where you're going to see, you're going to record your spectrum, it doesn't know anything about what's happening outside of the spectrograph. It doesn't know where your telescope is, where what you're looking at. So your guide camera has to be your eyes as well as your guider, and it has a little more importance in the setup here. This is just to illustrate some of the features of the Lhires. You have a calibration lamp and a flat lamp. It's just a simple switch. It requires a 12-volt power source. You can hook up an adapter to plug it into a regular outlet. This is what your calibration lamp produces here. If you take an image of it, it's a neon lamp, so it produces a bunch of emission lines in the red end of the spectrum. So your hydrogen alpha is going to be in here somewhere, and the neon lines you can see here, and they have the specific wavelengths, and those are used to calibrate your spectrum. So you got to tell your software which wavelength goes with which pixel. That's basically what this does. On the bottom here is a flat image, which kind of, in a way, looks a little bit like what we're used to seeing. This is a tungsten lamp, and it's just you take your flats at the end of the night. They're just about 8-second exposures. What cameras? The attic cameras are very popular, and I think the reason is because the sensor has a QE that's a little bit skewed to the red, and since you're imaging in H alpha most of the time, it does help you. But a bunch of different cameras can work. Starlight Express, ZWO, ASI cameras are great, but you have to look, when you look at this, okay, this is my guide camera, and this is your imaging camera. There's not really a lot of space in here for a lot of bulk, so you have to be careful with, things like SBIG and maybe some other ones that may be a little bit tighter. And also the unit only weighs about 2 to 3 pounds, so it's not really that heavy, and these ports are not really super well, they're not really built to accommodate a lot of camera weight, so you just need to be aware of that when you're setting this up. Telescopes generally want to match your optics to the focal length of your spectrograph, which is about f10. So in this range of f8 to f12, that works pretty well. Classic SCTs are great. Your C8s, your C11s. I have a C14. You can use RC scopes. You can pretty much use any scope as long as you realize that if it's going to be out of this range, then you're going to probably need either a Barlow or a focal reducer. So what are the things that you can observe? Well, you have to remember, high resolution, you're going to have a lot more dispersion, so it's going to dim things up a bit, and that's going to limit your magnitude to probably in the 8 range. So you're really going to probably be looking at stars mostly. And that's really where most of the research is at. Variable stars, the so-called BE or B emission stars, and binary stars, and occasionally novae are good targets. You're going to be probably doing H alpha for the most part, because that's where the strongest signal is in most cases. But you're not. There's nothing written in stone on that. You can certainly go to other regions of the spectrum that we'll get into in a little bit. So variable stars. So those are stars that have intrinsic variability from pulsation in a unstable atmosphere, changing in brightness at varying periods. So I just have an example of a typical spectrum of a spectral type A star. This is Hedera, which is in Gemini. It's like, I think, magnitude 2 or so. And this is a fairly typical absorption line profile that you see. Here's your 65, 63 point there. These lines here are mostly water vapor, nothing really special there, but just to give you an idea. And then, excuse me, on the left here, you see the raw spectrum, and here's your absorption line where the white arrow is, and I blew it up a little bit so you could see it a little easier. And that's definitely different than what you see on the bottom. So this is Rigel, which is a variable star. And what you notice is this line profile has what you call an emission wing here. This is a region of emission, and that's caused by stellar wind that's close to the star. And this is actually moving away from us because it's toward the red. And you have this material that is showing absorption, and that is moving toward us. So this sometimes is flipped. It changes pretty frequently. So it's a pretty dynamic system. And if you take spectra on a weekly basis, you see the changes that are pretty dramatic. This is a subset of stars. You're going to probably be spending a lot of time here. These are so-called B emission stars. They're a spectral type B that have a rapid rate of rotation, about 200 kilometers per second or greater. They form a large circumstellar disk, and so this on the upper right, this is my bad here, because this should be horizontal. This is one of the earlier ones that I took. But in any event, you see here's the absorption portion, and on either side of that, you see what's called an emission lobe. So on the bottom here, you get this kind of bilobed line profile, which is pretty interesting. And if you look at this schematic here, this kind of shows you what you can expect to see depending on the observer's location in relation to the star. So if you're looking directly down onto the star and you see mostly the circumstellar disk, you're going to get mostly the emission component because the disk is going to dominate. But as you shift over and start looking at it from the edge, you're going to get more of an absorption component from the actual star itself. So this was really cool. This was the symbiotic nova that blew up in August. I know some of you looked at it visually. This is a visual GIF produced by the imaging team of Guido Rocchetto and Valsavari. Hopefully I'm pronouncing that right. But this shows dramatic change that you can see there. And on the right is the spectral version. But the thing is, with this on the right, I was about a week and a half late. So this is just two observations, 2 or 3 days apart. And this was already about a week and a half after the peak. So what you see here is a very large emission zone this is the ejecta from the explosion. And this is the hydrogen peak, the hydrogen emission peak, and by now it's kind of lost in this continuum here. But you can see that this is a very dynamic system, and if you image this, if we were to image this every night, there'd be some significant changes there. The middle portion here this is a raw spectrum showing the emission, the raw emission spectrum, and then you can see this broad brightening here. But this nova is a binary, so you had your red giant and your white dwarf, and what was happening is the white dwarf accretes material from the red giant. It gets to critical mass, and that triggers what they call thermonuclear runaway, and that causes the explosion. So that was a pretty cool thing. Now, novae are not always visible with high resolution equipment because they're typically a lot dimmer than what this was. So this doesn't happen that often. We're just lucky to be able to see that. Well, what else can you observe? I mean, pretty much anything that you can see up to the limiting magnitude. The comets are very popular. This was Neowise, I think, and it was bright enough where you could actually get a spectrum of both the inner and outer coma. You can see the sodium emission lines. There's a cool project you can do where you can calculate the rotation of Jupiter by looking at the Doppler shift of the spectral line, where you have the blue shifted on one limb and the red shift on the other limb. So now with that, we want to know, well, how do you do it? If you were to decide to do it, this is my setup here, spectrograph, camera, and guider, and I have the C14 there on the left. So the key take-home points is if you're going to go with the Lhires and you get your spectrograph, you want to look at the solar spectrum with an eyepiece. It is safe to do that, by the way. There's not nearly enough light coming in, even at the zero order. There's no problem with that, and it's really cool to look at you kind of scroll through. You start from the blue end and you go to the red end. You see all the Fraunhofer lines, and you get to the red end. And the H alpha just kind of it's like three-dimensional. It's pretty crazy, but that tells you where H alpha is on your micrometer, and then you can write down the numbers so you know exactly where it is. So once you do that, you cover the telescope. You can look at the neon lamp lines, which are thin red lines that you're going to see in your field. There's usually 3, sometimes 4 of them. Most of your setup you're going to do indoors during the day. And the convention in spectroscopy is that in your image you want to have blue is on the left side of your image and red is on the right. The other thing to remember, because as we pointed out before, your camera doesn't know anything about what's outside in the sky. It's just seeing the slit image and light coming through that. So that's where you're going to work on your resolution, by focusing that lens in the spectrum, in the spectrograph, sorry. This is a spec diagram of the Lhires, and these numbers are really important. Once you get these right with your camera spacing, you're going to be fine. So we all know about things like metal back distance and back focus and stuff. This really has to be accurate to, I would say, really within a millimeter. If you do go with this spectrograph, the folks at Shellyak are great. They'll help you set your camera equipment up and get you the right adapters so you get the spacing right. But that's really critical. So the basics are, you're going to adjust your micrometer like we discussed, find your HA line, you focus the doublet, you got to get your camera orientation right. So blue is on the left, red's on the right. I screwed that up when I first started and had it backwards. So it's easy to do. Then you want to check your guider image and make sure your slit, the image of the slit, is correct. So like we said, find your HA line, look at your neon lamp lines, make sure you see them. So that tells you that yes, you are in the HA region. This is our old friend Nyquist, who's coming back to haunt us here, but it's actually a lot different because we don't really care about the sky scene. What we're interested in is that light coming through the slit. So that's 23 microns through that slit. And for myself, I'm using an attic camera. The pixels are like 4 microns, 4.5 microns. So I'm going to bin, and so the light coming through the slit is going to fall on 2 to 3 pixels with this this relationship. So the nice thing is you have control over that every night, and all you have to do is focus the lens inside the spectrograph. And what you do is you take an image of your lamp, and we'll talk about the ISIS program, which is really great. And what you do is you draw a little rectangle around your line here, and you click on, there's a full width half max button in the program, and it tells you, okay, your X is, well, in this case, we're good because we're 2.87, but let's say it's 4 or 5 or something like that. You're going to need to go back and just refocus it until you get that number right. And that might take about 15 minutes or so. This is an example of doing that out at the telescope. The doors of the side doors of the spectrograph are removed. Here's your doublet ring. There's a little nylon ring. You have to unscrew that. You got to take off both doors to get it right, so you can turn the ring easily. Then when you're done, you just tighten everything up. This is a image of your calibration lamp. Here's your 3 lines that you need to be able to see. And notice that they're a little curved. That's because you got that 10-degree tilt in the spectrographs with the light coming back toward the camera. But the good news is your software is going to cure all that. You don't even have to worry about it. So this is what I mean with the lamp image. So you go in your ISIS program, and here's your image tab, and you just draw a little box around. This is the center line of the 3, or not center, but it's the middle one, because that's the one that's closest to the center of your sensor. So then you come over to this full width half max button, click on that, and okay, we're good here. So that's what you're going to do to get that focus. You only have to do it once, and it's good to practice it indoors, but like with our regular cameras, we have to refocus because the temperature changes. So you're going to want to do that at the telescope. This is another way you can check your camera orientation. So again, you got your 3 lamp lines here, 6506 on the blue end and 6598 on the red end. So that is correct. When I first did this, these were flipped. I had the 2 on the right and the one single one was on the left, so that was not correct. And that was easy to recognize, and I fixed that. Here's the HA line. So what you do is you go out during the day, point your scope at a random part of the sky, and you get the reflected spectrum of the sun. So here's your HA line, and you turn your micrometer counterclockwise, and that will move you into the red portion of the spectrum. So you're going to want to see this line move to the left. So it goes the other way, your camera's upside down. So that's another clue that you can use. This is your guide or slit image. Okay, so this is pretty ugly, and if one of my mentors is watching this right now, he's probably cringing. But this was about 2 weeks before the conference, so I was not about to go into the spectrograph and monkey around with it. I was able to confirm that this slit is about 2 pixels, which is what you want. It goes through the crosshair, so I can find it at night. But I left this the way it is. I promised that I fixed this, and this is not the way it looks now. But I left it for this talk because here you can see the edge of the slit mirror. Okay, so this totally worked for my setup doing it manually. But to be fair, if you are going to do a little more automation, you're going to do plate solving and kind of the same routine that we do for imaging. This is going to have to be improved where it lines up with your guider better. But the main thing is you want the slit image to be about 2 pixels, And the way that happens is your distance between the spectrograph and the guider is in that 1 millimeter, not more than 1 millimeter off of that back distance that you need to get right. This is the guide port here. It's pretty small. It's weird. It's like a C mount, but you can find adapters for that without too much trouble. So at the telescope, you're going to refocus a doublet because the temperature is going to change. You want to do that one time. You're going to focus the telescope. Now I just focus with the knob on the primary mirror. That's all I do, that works great. And you want to make sure the spectrum is horizontal and in the center. Your workflow, what you're going to do is, first you got to slew to what's called a reference star. So what happens is your equipment has a certain spectral sensitivity. It's going to be different for every observer, and you want to correct that in your final spectrum or account for that. So you're going to take your reference star spectrum. You're going to compare that to a database of professional spectra, and that's going to be used to calculate what's known as your instrument response, which gets figured into the final target spectrum. Now, these are the things we're used to. Obviously, you want to center your target. You center the star on the slit. You start auto guiding. You don't want to oversaturate. Then you take your calibration lamp image. Then you go to your target star, repeat the process. And at the end, you take your calibration frames, your darks, your flats, and your biases. So this is just an example of what it looks like out in the field here. Here's the edge of that slit mirror. Here's the target. This black arrow is actually the center of the sensor that I figured out initially. Now it's more like here because I adjusted the mirror, but this worked. I mean, as long as I knew where this was, I would just jog move the star down to about this location and just take a test image and make sure that it was centered. And you can see this is a pretty big guider field, and you have a bunch of guide stars that you could use. So you got to. So that really does help if you have a large guide field that you can take advantage of. This is an example of a reference star. This is a super bright. This is probably Vega or Altair or one of those. And the thing is here, the eye is an excellent judge of when, in my opinion, when this is centered. Because when you do that, when it's centered, you're going to see this line is going to darken. The slit line is going to darken, or you could say that the star dims. But what your eye sees is that this all of a sudden gets dark because the flux of the star is dropping as the maximum light that can get through the slit is going through it. So then you know you're good. You got a nice little guide star here that you can use, and you're all set. This is your lamp image that we talked about before. This is your target star. And since I do this manually, sometimes your pointing may not be that perfect. And I find that if you use your field of view, if you have a field of view indicator that shows what you should be looking at, you can see the pattern of stars that you should be seeing. This is not related to what you're seeing here now, but it's just an example of something that can help you. Now you're going to be looking at mainly, stars that are, they're pretty bright. I mean, they're going to be like 6 magnitude or so, and they're going to be the brightest star in the field by far. So you're going to be able to find it pretty easily. So how do you process a spectrum? This is the ISIS program. It's written by Christian Buil, and it's an excellent program because it takes it automates just about everything, and it's very simple to use. This is a one-page tutorial. That explains everything. So you can go to this web page and get all that information. The key thing is you want to put or set up a folder that the program knows where to find everything. And really, it's just one folder anywhere, and you put everything in there. You put your flats, your lights, your darks. You don't have to organize them in any way. If you don't want to, it can be like a closet where you just throw all your clothes in there. They don't have to be folded. They don't have to be organized in any way, shape, or form. They just have to know that they're there. So you set that up here in this working directory. When you go to the spectrograph model, this is really cool because if you click on Lhires, it tells the program, okay, I'm using the neon lamp lines, 6506, the other two, and it already tells the program that's how you're going to calibrate your spectrum. So you don't really have to do much more than that. And of course, if you need the program in English, you click on that, you reboot it, and you should be good there. So you go to your Masters tab. Everything you do in here is clicking on a Go button. That's how you get through this. So you name your master files however you want to, and you click on Go, and it produces a master file with this name, and you get all your files in the same spot, and it knows where to find them. Then you go to your General tab, and really the key thing is you got to name your object and put a little hyphen next to it. Otherwise, it won't recognize it. But that's all you need to know there. It tells you all these things, your location, how to set that up. In the tutorial, it takes maybe about, once you set it up, which is about maybe 15, 20 minutes, you can run through this in a few minutes every time you do a spectrum. You go to your calibration page, and what you're going to do is you're going to use this grid here. This is called the graticule, and you can click on and off of that. So you want to get these inner lines as close to your spectrum as you can to eliminate the background noise. That's why, as you can see, you're going to need to make this pretty horizontal, because if you have more of a diagonal one, you're going to need to spread these out, and that's going to include a lot more noise there. Next, you're going to figure out the tilt of your spectrum, how far off of horizontal it is. That's pretty simple too. You draw this box, click on tilt. It goes right here, calculates it. You're done with that. Next, you go to your calibration image, and you're going to calculate the slant. As we mentioned, it has that curved, it's a little bit of a curve to it, and you want to correct that. So you draw a little box around here, click on slant, calculates that. And then the key step here is you're going to, on this line, which is the 6506 line, that's the furthest away, furthest in the blue, you're going to double click here, and that's going to tell the software, okay, this wavelength is at pixel 200. So you're going to do that. What I want to do is just, we're almost done. I'm just going to run through this processing here for 2 minutes, just to kind of give you a sense of that. So we are going to process a spectrum of Vega, and notice I have the star has the dashed line in it, and it knows exactly, okay, you've got 8 light frames, and if you click on this box, it confirms that it's 8. So next you go to your calibration page. So I'm going to move this down to the center here. Here's your grid, and oh, I don't see any spectrum. Well, that's because you got to take this slider and you move it to the left here, and presto, there's your spectrum. So the next thing you do is you're going to center it. You just double click in the center there. The next thing you do is you take the grid off and you draw your box, and you calculate your tilt. And the next thing you do is go to your calibration file, and you're going to set your wavelength here on the edge. Tells you you're at 204. You're going to draw your box around the middle line, calculate your slant, puts that in here. Okay, now we've set everything up. So what do you do when you want to process your spectrum? Well, you click on Go. And in a few, about 10 seconds, your spectrum is processed. And that's it. Well, of course, now, okay, what it does is it takes a two-dimensional spectrum, okay, and it converts it to a one-dimensional, it's almost like a data file, because what it's doing is it's assigning intensities of the spectrum to each pixel. But there is a profile that you can see, because what you do is you just click on this profile and display, and there it is. So, and here's that is 65, 62.5. So that's how you process the spectrum. Now, this was your reference star, and you're going to go through that again after you figure out your instrument response, but that's another, let's say, 10 minutes of that. So now that you've done that, how do you submit it? You're going to look for this 14 kilobyte fit file. Okay, that it's not the two-dimensional line profile. You're going to send this to your sources, and you're probably going to start with this. This is the best database. It's probably the biggest one in the world for BE stars, and this is great because when you submit your spectrum, you get somebody to tell you, okay, it looks fine, it's accepted, or if it's not accepted, they'll tell you what's wrong with it, and they'll give you hints on how to correct it and what to do, and that's a great learning experience, and it's great to help you get better at the spectrum acquisition side. The AAVSOs we talked about. This is a great resource. And you can do the same thing. They have a spectral database. You can submit any spectrum you want there. It's also great because they have a forum there. Great people. They answer all your questions regardless of how simple they might be. So you definitely will want to do that. So pro-am collaboration, that's a big thing with the high-res spectroscopy. But really what happens is not you seek them, it's they're going to seek you out. The AVSO is the resource for even the NASA telescopes. They really need people to support. They need ground-based support on their research all the time. So there's never a shortage of projects to do. You can also join these groups here. Astronomical spectroscopy is great. Spectro-L and ARIS is a spectroscopy group in France. If you want to learn more, this is the book to get, written by Francois Cochard, and it's indispensable. Kind of goes through some of the stuff that I presented in much more detail. So you definitely want to do that. And that's pretty much all I got. If you want to find me, you can find me on Dave and Telescope at WordPress. That's my blog. I'm also an active member of the Astronomical Society of Las Cruces, which one of you mentioned was founded by Clyde Tombaugh and has a rich history of education and public outreach. If you're in southern New Mexico, you need to check us out. We do a lot of cool things there. Thanks a lot, and I'll take any questions you have.
I don't see any questions in the chat, but I have a couple of questions. So the reason that your data is so valuable is that the professional astronomers just have difficulty getting telescope time?
Yeah, well, that's certainly that's got to be a part of it. I mean, they have to apply for telescope time, a year or so in advance. They get maybe a night or two, and that's it. And then it may be cloudy. Who knows?
And
so yeah.
If someone wanted to go into this, what would be the cost of just the spectral equipment?
So okay, so the Lhires, the spectrograph, new, I'm thinking is it's probably 2,000 to 3,000. But there are a lot of used ones out there now that you can get for under 1,000, and there are also probably kits. Because this started out, the Lhires started out as a kit that you could put together before they made it a compact unit. So there are other less expensive options. And as I mentioned before, there are groups that are 3D printing these things. So I'm sure there are avenues that people can take that are less costly. That's really your main expense. I mean, ideally, you could use a telescope that you already have, but the telescopes that you need, you certainly could get, I think, pretty easily.
So when they say you 3D print, you're not printing the grading, I'm sorry.
Oh, the grading. Yeah, you're not printing that. No. I mean, I don't imagine that you're printing that.
I don't imagine you're printing a gradient.
You're not printing the grading. No, I don't. I don't think you're doing
5,000
that.
lines per
Right.
millimeter.
Eric, if you could give me a second here. Lanceman says he pointed out relatively early on that it looks like the telescope focal length may not really be an issue when performing this type of astronomy. And then later on, Pam and Jeff, who are already planning a consortium to take on high-res spectroscopy here, Pam says that she might need to wait for a bigger scope, though. Tell us about what kind of scopes we need, what the implications are, and that stuff. I think you touched on it, but tell us again.
Yeah. Okay. So, so you basically need to match the. So the spectrograph has the folded focal length is f10, and you want to match that more or less with your telescope optics. So you want to be within that f8 to f12 region, but you don't. I mean, you could, like, if you have a f5 or something like that, you could use a Barlow to. I'm not really sure how that works though with your cameras, etc. But I know that people do that or can do that. In terms of aperture, your stars are they're pretty bright. So you're probably not going to. I mean, I think you're still going to be able to see to the magnitude limits. Your resolution might be affected though, depending, and that depends on also the slit width. It's a little more technical because there are different size slit widths, and you might have to match them, with the telescope that you're using. Typically, a 23 micron will work with, I think, just about anything. So you could use a C8, you could use a C11, you could use a refractor even.
Okay, you've been speaking of focal lengths, not focal lengths. You've been speaking of f ratios, and that can vary dramatically according to your aperture. What kind of aperture do you need on these things?
I don't think that the aperture is is a limiting for high res. I think I would say, just from what I've seen, probably 8-inch would be your.
You'd go for one of the. You'd go find somebody's used Celestron C8.
Yeah.
And take it and to go from there. Okay.
Right.
Don and Paul and Elizabeth Romero, and I guess everybody else in the whole room there with them. Do we need to use non-anti-blooming camera mono cameras? What kind of cameras do you use?
You use well, I have an Attic 460EX, so I believe that is I think there is I don't think that's non-anti-blooming. I don't think so.
And I suppose it has to be somewhat linear.
Yes.
All the way through.
Yeah. So I don't know. I think everybody that I've seen is still using CCD. I don't know about CMOS. I think CCD is still preferred.
Okay.
Probably because of the linearity.
Yes. Yeah.
Dave, can I
But it wouldn't take a brand new, hottest off the market CCD. It just takes something big enough chip to see the results, right?
Right.
Dave, can I ask a question?
Yeah.
I see you have a reasonable amount in your photograph there. How do you find and verify the star of interest? Are you looking through the slit while doing this, or is there a way to see the full background of stars in plate solve?
You can definitely plate solve, and there are a lot of people doing that. But if you're looking at stars, you know, I haven't imaged the wrong star yet, and I've done this manually. I don't plate solve. I kind of if I have to, if I'm looking at a star on the dimmer side, let's say, you know, closer to magnitude 8, I would rely on my, you know, my FOV in my planetarium program to say, okay, that's the pattern of stars, and this is the star that it should be. And the other thing is, if you're, let's say you're imaging a B emission star, well, you're gonna want to see an emission spectrum. You're gonna take a test image, and if you don't see emission in the hydrogen alpha line, then you might think, gee, I wonder if maybe I don't have the right star. So there are things like that that can give you clues to avoid that mistake. But typically the star that you're looking at is going to be a lot brighter than the background in your field.
And you do all of this initial setting up your scope through the slit, do you?
I'm sorry, say again?
This initial, I guess, finding the star, you're doing this through the slit?
No. Your guide camera, because you know that the light that goes through the slit is not going to help you in any way other than
I see.
that,
Okay.
you know. It's the light that's reflected off of the slit, because the slit actually sits in the center of this mirror, and the light is going to go back into your guide camera. So that's how you're going to know where you are.
Okay, thank you.
Yeah.
And actually, Jim said that he uses CMOS cameras, and they work just fine for this application.
Okay. Well, yeah, that's great. I didn't really know anything about that, to be honest.
That would change your sensitivity, probably.
Yeah.
Wouldn't it?
You know, I guess I got an old story out of my past. In my club, I was the junk dealer. Whenever we got something donated to us that we needed to unload or something like that, I was often asked to do that. And one of the things I was asked to sell was either a C9 1/4 or a C11 or something like that. And when I was meeting up with the guy to sell it, and I says, look, I can't guarantee any of this or that or the other thing, but I know it works pretty well. And I don't know about pretty pictures or what it takes. He says, I don't worry about that. I'm doing scientific stuff, so I don't really have to push it. And that may be why so many people with CCDs on the attaching them to their you know, their things, their instruments there. That may be why. It's because these do not take the highest, lowest noise, all the things that we look for when we're doing our pretty picture astronomy. Is
Right.
You can get by with really decent, just good old-fashioned pedestrian equipment.
Yeah.
Well, probably because you're just looking at a single star in the center of your field,
Mhm.
right? You're not worried about what's at the corners.
Yeah, it's true. I might have to
Yeah.
put my C11 back into service. I was
Yeah,
gonna
right.
look at selling it, but
All
there you
these
go.
old SCTs that we have in the telescope museums in our basements, we can take out for this kind of project.
That's right.
Okay, I think we've got the questions. We've marked them all off. And I think we got them all in. We want to thank you very much for introducing us to another world. I think you got a few converts there. Jeff and who is it? Jeff and Pam will be doing something, and there's a few other people commenting. So
All right.
looks like we got something going for you here. Okay, Dave?
Great. That's awesome.
Okay. Well, that's probably getting pretty close to it for tonight. I think we've got all the questions in. I just want to say happy Halloween coming up. Dress up as something really spooky and enjoy yourself. I mean, on Halloween especially, don't forget to wear a mask. And what else? I guess that's it. Who's in charge? Tim?
You can dress up as Cloudy Night. Be spooky.
Okay, Tim, take it away before we start having more dress up ideas.